So I wanted to go ahead and go through the challenge problem circuits that we gave you guys last Friday. So the circuits are not hard with nodal analysis. In particular, you'll see the challenge circuit gate that we gave the second circuit is actually not even a system of equations that you have to solve. This one is a little challenging, but I'll walk you guys through how to solve it. So in nodal analysis, what we need to do is identify the nodes that we're trying to solve for. So I'm going to go ahead and circle all the nodes in red. So we have one node right here, right? That's the ground node. Remember, a node is anywhere that is just connected purely by wire. Because anywhere that's connected by only wire will have the same voltage at that point, right? So we have one node right there. We have another node right here. And in fact, I should be drawing this whole thing we can call the node. We have another node right here. It's all one node. We have a node right here. And are there any other nodes? No, there aren't. Okay. So the task in nodal analysis is to find the voltage at every single one of these four nodes. Okay? If we know the voltage at the four nodes, we've solved the circuit. Now, as it turns out, we didn't write where ground is in the circuit, so I can put ground wherever I want to make my life easy. Since we've drawn the circuit like this, it's going to be easiest just to put the ground at the bottom, right? And so ground is 0 volts. That's by definition, okay? So now we need to find the voltage at this point, and at this point, okay? And to do that, in nodal analysis, we write Kirchhoff current law expressions for each node. We write the current going into each point equals the current going out of each point. Let me go ahead and erase these red dashes. Do that. Okay. So, first of all, we have current sources. Current sources literally just dictate the actual. I realize I didn't label that resistor. Let me figure out what the value of that resistor is. That's a 1 ohm resistor right here. So 1 ohm. Okay. Current sources force the current flowing through them to be whatever value that current is. Okay. A voltage source gains voltage. So this voltage source, I believe, I should have labeled that as a 2 volt voltage source. This voltage source, we go from here to here and gain 2 volts. Okay, but we don't have 1 amp here and then gain 3 amps there. That's not how a current source works. It just makes the current along this stretch, it makes that current be 2 amps. Okay, so that was maybe unclear. I know we didn't discuss that in lecture, but that's what a current source does. So let's call this node VA. That's the voltage of that node, V sub A. We'll call this node V sub B. We'll do this in a different color, actually. So this node is V sub A, this is V sub B, and this is V sub C. Okay? VA, VB, and VC. So we want to write the currents going into each of these three nodes in terms of VA, VB, and VC. Okay? But VC is just 2 volts less than VB. Notice how there's that 2 volt battery in between them. So VC, then you go through the battery, gain 2 volts, then you're at VB. So instead of writing VC, I'm just going to write VB minus 2, right? Because when we go through the battery, we gain 2 volts, and then we're at VB. Okay. So now I only have 2 variables left to solve for. Now let's look at this node right here. The current going into the node is 2 amps. Okay? Then I'm going to say there's 2 currents going out of this node. Okay? So this current right here is going to be dictated by whatever voltage divided by resistance is on this resistor, right? Because that current is the same as this current. this current and that current are the same, right? They're just along the same wire. So the voltage before the resistor is VA, and the voltage after the resistor, if we trace that wire, is VB minus 2. So the voltage drop is VA minus VB minus 2. That's the voltage drop. And that means the current is that voltage drop divided by the resistance, which is just VA minus VB minus 2 divided by 3. Okay? Remember, let's back up and remember what we did there. Took the voltage before and the voltage after, subtracted them to get the voltage drop, divide the voltage drop by the resistance to get the current. And we did the voltage before minus after because we're looking at the current in this direction. Okay? If I drew this arrow going in this direction, I would need to make sure to do the voltage here minus the voltage there. Everything would still work out the same. I would just get a negative sign. But in the end, my answer would be the same for this problem. Okay, it's all good. Now, for this current, the voltage before the resistor is VA, the voltage after the resistor is VB. So the voltage drop is VA minus VB, and divided by the resistance to get the current, so divided by 1. That's the value of that current. Okay, so now we have the current going in and the current's going out. So we can write our equation. 2, which is the current going in, equals this first current right here, VA, and I'm gonna distribute that negative into the parentheses, plus 2 minus VB over 3, plus this one, plus VA minus VB, plus VA minus VB. Okay, so this is our first equation. Okay, that's equation 1. Now let's derive our second equation. Okay, our second equation, we have an option here. We can either look at this node or we can look at this node. Because remember, these two nodes are represented by the same variable. So we just need to come up with the second equation. If we have two variables, we need two equations, right? It doesn't matter if I get that equation by looking here or looking here. But if I look at this node, I have a current source at this node, right? And a current source always makes our life easier in nodal analysis because we have a number. There's no variables involved with the current source. It tells us exactly the number of the current going in or out of that node. So I'm going to look at this one right here. We have, and we're just going to treat this entire thing like it's one node, okay? I'm going to like even color that in. So you have some current going into the colored in thing and some current going out of the colored in thing, okay? So let's say that we have this current going in. Let's say this current goes down, because it's always easier to say the current goes out of the node, except for our current source, because it tells us the direction already. And so the current is going out in that direction. Okay? Oh, and it can also go in this direction. Okay? So, now what we need to do is figure out what each of these currents are. So this one's easy. It's just 3. Easy as pie. This one's also easy. So we have the voltage before is VB minus 2. The voltage after is VA. So the voltage drop is VB minus 2 minus VA. The resistance is 3. Now notice, this term is just the negative of this term, right? This is just the negative of this term. And that makes sense. We just do this arrow in the opposite direction, okay? And that's completely fine. It doesn't matter what direction we draw the arrow, because all that happens is we just get a negative. That just ends up there, okay? Everything still works out the same if we're consistent with our signs and our arrows in a given equation. So we have that current. So put an arrow like that. Okay. This current's also easy. So we have So see that? Yes. The voltage drop is VB minus 2. That's the voltage before. The voltage after is just at ground, so minus 0. I'm not even going to write the minus 0. And then divided by 1. So divided by 1. Okay. But now we have this current right here. How do we solve for that current? Well, let's just call it a new variable. Let's call that current I. Okay? And let's try writing out an equation for I. Okay? So I has to equal this current plus this current, right? If I flows into there and these two currents flow out of there, I has to be equal to these two currents flowing out of there. If we write those two currents, then we can just write what I is. Okay? So this current is VB over 2. Okay? The voltage before is VB, the voltage after is 0, and the resistance is 2. Voltage drop is VB, the resistance is 2. VB over 2 is the current. The current in this direction, the voltage before is VB, the voltage after is VA, the resistance is 1. So that's the current. VB, the B is kind of sucks there. VB minus VA over 1. Okay? So, I equals VB minus VA over 1 plus VB over 2. That's our second equation of interest. Okay? And we can write a third equation as well. So the current going in is 3. 3 equals, this current is VB minus 2. This current is VB minus 2 minus VA over 3 plus VB minus 2 minus VA over 3 there. And the last current is just I plus I. Okay? So now we have a system of 3 equations, and we can go ahead and just do some algebra. I'm going to move a little over here to show you how to do this algebra. Oops, there's some stuff on the board. Okay. So, these are our 3 equations. We have a system of 3 equations to solve, okay? But notice that this equation tells us what I is. So I'm just going to substitute that into this equation right here. Okay? So we have 3 equals VB minus 2 plus a VB minus 2 minus VA over 3. VB minus 2 minus VA over 3 plus I. And I is just, from here, VB minus VA plus VB over 2. This looks nasty, but there's a lot of simplifying that we can do here, okay? So, okay, we just substituted in I. Now let's go ahead and simplify this equation. So I'm going to leave this term, actually, I'm not even going to simplify it yet. Look at this equation. So first of all, this term is just the negative of this term, okay? In fact, this term is also just the negative of this term. So I can just add these 2 equations together and I'll get rid of a lot of the nastiness. So let's do that. If we add the left-hand sides, we get 5. 3 3 plus 2 equals 5. If we add the right-hand sides, this term cancels out, this term cancels out, this term cancels out, this term cancels out, and all we're left is VB minus 2 plus VB over 2, which is just 3VB over 2 minus 2. Okay? And now we can solve this pretty easily, and we just get VB equals, so add the 2, you get 7, multiply by 2, you get 14, VB equals 14 over 3. Okay? So is that reasonable? Does that make sense? Well, that's when you then go to LT Spice and check if your numbers make sense. Okay? I'll just tell you the numbers do make sense there. Okay? So VB equals 14 over 3. That's about 4.67 volts. Okay? Now what the problem asks us to solve for, if we go back here, so actually before we continue, VB equals 14 thirds. Now we can easily solve for VA. Okay? We can do that by looking at any of our equations here. For example, this equation is probably the easiest. Since we know VB, we just plug in that value and then solve for VA. So 2 equals VA plus 2 minus VB, which is just 14 over 3, over 3 plus VA minus 14 over 3. Okay. So now it's a little bit of algebra, which we'll just do. So we multiply by 3, 6 equals VA plus 2 minus 14 over 3 plus 3 VA minus 14. Okay. So let's subtract 2, add 14. So let's add 12 to both sides. That gets rid of this and this. We get 18 equals 4 VA minus 14 over 3. Now we add 14 over 3 to both sides and then divide by 4. And you can use a calculator to do that if you need to. What we'll get the answer is, we'll get the answer as 54, 14, 68 over 3. 68 divided by 4 is just 17 over 3, I think. So VA equals 17 over 3. So we have VA we solve for and VB we solve for. In other words, VA is a volt higher than VB. Okay. So now that we've solved for those voltages, all we need to do is go back to our original circuit and just do P equals IV for this, P equals IV for that, and P equals IV for that. Okay? So it's a little bit involved, this circuit, and it's definitely challenging. And you really need to flex your nodal analysis muscles on top of your system of equations muscles. If you need to solve the system of equations with just an online solver, that's also completely fine. Okay? That is completely acceptable, and we encourage you to do that. However, on actual applications or tests in ScioVirtual or whatever else, it's good to be able to solve these things by hand. And adding equations together rather than try to do with rote substitution is always a convenient and good method to try. So that's that one. All right. So for the so-called challenge circuit, really this is just an approach, a problem of understanding what you're actually looking at and not just trying to brute force the equations. Because if you try to do nodal analysis, it'll get a little confusing in your head just looking at the original circuit. It's actually completely doable, and that is what you could do and successfully solve the problem originally like that. But you'll have to think about a supernode and, other terms that you can throw around like that. But it is completely doable with what we've taught you. However, what you should notice if the camera stops tweaking out is that we don't need to draw this huge looping connection all around like that. The relevant nodes here, let me get my color, the relevant nodes in that connection are right there. Oops, sorry, not right there. I don't know why I would do that arrow. What's that? Right there. All right. Here and right here. So if you kind of visualize in your head, if I, not right there. Sorry, I'm all over the place right now. All right, there and right there. So really, there's no reason for me to draw this on this side. I can just put this whole thing over here, and as long as I keep all the connections between elements the same, it doesn't matter where I draw them, as long as the connections are the same. So I'm going to go ahead and redraw this circuit. Okay? I'll take you with me as I do this. So, first of all, why is the camera doing this? Okay. So, the battery's still cut off. Okay, we good? Hello. Okay. So, let's focus on this branch that goes all the way around first. I'm going to put the 5-volt battery in the middle. Okay? That's 5 volts. Then it goes up. And I'm going to draw this whole branch now to the left of the battery instead of all the way looping around. Okay? So we have a 5 ohm resistor, 5 ohms, and a 20 volt battery, 20 volts, and then a 30 ohm resistor, 30 ohms. So this connection, which is 30 ohms up to the 5 volts, is still preserved. 30 ohms up to the 5 volts. This connection, 5 volts up to the 5 ohms, is also still preserved. Okay? So now let's draw in the rest of the circuit. You have a 10 ohm resistor, like this. So 10 ohms. Okay? That goes down with the 5 ohm resistor. 5 ohms. And then to the right, we have another 10 ohm resistor. I'm going to get cut off soon, but 10 ohms. And then a 10 volt battery. And a 30 ohm resistor. 30 ohms. Sorry, 20 ohms. 20 ohm resistor. 20. Okay. So these circuits have the exact same connections. If you need to pause here and take a look, take a given component, look at what's to the right and what's to the left. Okay? You should notice that the connections between any given circuit elements are still the same. There's no elements that are newly connected to each other or newly not connected to each other. I've just redrawn it in a way that makes the nodal analysis that we need to do at this point and this point a lot more obvious. Okay? So let's go ahead and proceed with that nodal analysis. Okay? So, step 1, I'm going to go a little quicker than I did on the first one, but first we set the ground, and ground is 0 volts. Okay? Now the relevant nodes that we need to figure out the voltage of are going to be this one primarily and this one primarily. Okay? Now you may say, but Ishaan, we have a node here and a node here, and a node there and a node there. But instead of forcing ourselves to look at all these extra nodes, we can combine these resistors in series because they have the same current flowing through them. So I don't need to draw that. I'm just going to put a wire there, and I'm going to put a 30 ohm resistor here. Because remember how series is defined. If the same current flows through the two resistors, then they're in series. The same current flow through them, so there's 30 ohms. Add them together. So the same thing here. The same current flows through these two resistors. So I'm just going to write this resistor as a 35 ohm resistor, and I'm going to get rid of this guy entirely. Okay? I can't do that with these three, because the same current doesn't flow through these three resistors. It's a different currents between them. Okay? Now, we already know the voltage at this point, okay? If it's 0 here, we have 5-volt battery. That's 5 volts right there, okay? We also know the voltage at this point. That's 20 volts. Again, 0 volts, 20-volt battery, that's 20 volts. We also know the voltage at this point. It's just 10 volts, okay? But wait, there's only one node left. There's only one node that we don't know. So actually, there's no system of equations in this problem, unlike the last one. Mathematically, it's easier. You just have to apply a little bit more circuit intuition to get to that answer, okay? So let's go ahead and call this node voltage V sub x, okay? Then we have current going in this direction, in this direction, and this direction, okay? In this direction, it's Vx minus 5 volts over 10, okay? That's this one right here, going that way. Vx before, 5 after, so Vx minus 5 divided by 10 to get the current, 5. Going down, it's Vx 0 divided by 5, so plus Vx minus 0 over 5. And going to the right, it's Vx minus 10 over 30. Vx minus 10 over 30. Okay? And those are all going out. There's nothing going in. So that just equals 0. Okay? Now we just solve for Vx. So multiply the whole thing by 30. You get 3Vx minus 15 plus 6Vx plus Vx minus 10 equals 0. Okay? Add 25 to both sides to get rid of the constants. We get 10 Vx equals 25, or Vx equals 2.5 volts. Okay? So we have that this voltage right here is 2.5 volts. Okay? That's a decimal right there. 2.5 volts. So now, what we needed to find originally was the current through each of this battery. We needed this current, we needed this current. I'll use a different color now that I'm on this step. We needed this current. Oh, it's terrible. So we needed this current, we needed this current, and we needed this current. Because remember, we're inserting the total power supply to the circuit. Okay? So this current is easy to find. This one right here. 10 minus 2.5 divided by 30. Remember, we're inserting the current in this direction. So we do this minus that voltage. 10 minus 2.5 is 7.5. So 7.5 volts over 30 ohms. Okay? And then that's the current, equals, that would be 0.25 amps. Okay? That's in the direction of the battery, from negative to positive. That's the direction the battery wants to supply the current, or supply the voltage, I should say. So 0.25 times 10 is plus 2.5 watts. Okay? For this one, we can do a similar thing. Okay? 20 volts, we're inserting the current in this direction, in that direction, curve that arrow, right? 20 minus 5 is 15. 15 volts divided by 35 ohms gives us 15 over 35 equals 3/7 of an amp. That's in the direction of the battery, so 3/7 times 20 is 60/7, which is about 60/7 is about like 8.4 something amps, okay? Or 8.4 something watts. So 20 times 3/7 equals about 8.4 watts. Again, this is positive 8.4 watts because the battery is supplying that. It's not absorbing any power here. Now, the annoying one, unfortunately, comes for this battery right here, because we can't just do 5 volts divided by the resistance. There's not resistance there, but there is current flowing through this battery. So we know the current going into this junction, which is about it's about 3/7. It is exactly 3/7 amps. Okay. We also know the current going in this direction. 5 minus 2.5 over 10. So that's 0.25, or I'll say 1/4 amp. Okay. So this current just needs to make up the difference. What is 3/7 minus 1/4? That is going to be 12/28 minus 7/28, so 5/28 of an amp. Okay, 5 over 28, and it's going to be flowing in this direction actually. Okay, so 3/7 going in. 3/7 is equal to 12/28, right? 12/28 going in. 7/28 going out there. So the other 5/28 has to go down there. Now the numbers don't really matter, but since it's going in the opposite direction that the battery wants it to go, this battery is going to absorb power. So this guy's actually going to be negative 5 over 28 times 5 volts, which gives you about negative 0.9 watts. Okay, so 2.5 minus 0.9 is about 1.6, plus 8.4 is about 10 watts. So roughly, the circuit supplies about 10 watts of power. You should calculate the numbers exactly, check your answers in LT Spice, but that's what we have here. And so what I want to emphasize is, started with this nasty looking circuit over there, but it's actually not that nasty. Okay, we only had to actually solve one equation for one variable. So when you look at a circuit, don't just brute force go straight to the method. Think about what's actually going on and see what simplifications can I do before I start trying to do some math. Okay, you can save yourself a lot of time and effort if you do that. All right, so I also wanted to just show the LT Spice simulations here. So actually, I'm just going to redraw the circuit, okay, for educational purposes. So to add a current source, I just press P, type current, and I can add it, and use Control R to rotate it. Then I can add a resistor, another resistor. I can add a voltage source here, another resistor, another current source. Oops. Here, another resistor up here. Should be good to go. Up and through it and down. I realize this guy is not in there, so I just press M to move it in line. Then go there, then go there, and go there. Okay. And then I just have to type in the values. So we have a 2 amp source, 1 ohm. We have 2 ohm, 2 volt, 3 ohm, 3 amp, 1 ohm. Okay, now I'll get rid of this. I will add a simulation. You can just type a spice for .op, or you can just do this. So now it simulates it, and we can go through voltage there, voltage there, voltage there. So first of all, these are the values we calculated, right? We calculated the voltage at this point. This was what we had as, I think, VB, and we calculated VB as 14 thirds, or 4.67. Calculated VA as 17 thirds, 5.67. And of course, the voltage right here is going to be just 2 less than the voltage there because of the battery. So it all makes sense, right? Should that current go through there? I don't know. I think it's fine. I think actually this should connect there. But anyways, so this guy dissipates negative 8. In other words, it supplies 8 watts. This guy dissipates negative 2.6. In other words, it supplies 2.6. And this guy dissipates negative 11.3. In other words, it supplies 11.3 watts. So this is just how you go through and simulate a circuit in LT Spice. We calculated all these things ourselves, and if you wanted to verify your calculations are correct, this is how you do it. And so if you're doing some Science Olympiad prep and you want to do some circuits practice, but all the stuff online isn't good, this is your tool. Draw some crazy circuit on here. try solving it yourself. And then go and check your answers just by doing it in LT Spice. You don't need to find practice tests and stuff. The best practice is just drawing something random and solving it yourself. So I also want to show the other circuit. So let me delete that. So the other circuit, we had a 5-volt source there. Then we had a 10 ohm resistor here. Then we had a 5 ohm resistor. Then we had a 10 ohm and a 20 ohm resistor. 10, 20. We had a 10 volt battery. We had a 30 ohm resistor out here. And a 5 ohm resistor up here. And then 20. Now we just connect all these guys up with wires. The nice thing about LT Spice is you have keyboard shortcuts for all these things, so it makes drawing the circuit nice and quick. Okay, I think this is the circuit. 10, 25, 20, 30, 5, 10. Yes, we're good to go. So now let me add a spice. You can also just press dot, the period sign on your keyboard, and the type dot op. This adds the spice directive for the simulation. Let me run it. Okay, so first of all, that was the voltage Vx that we calculated. Remember, we redrew this whole branch of R6, V3, and R5 on the left. But all we did was just redraw it. So the actual node is the same. The voltage there is what we calculated, 2.5. The voltage supplied by this guy is about 0.9, this guy dissipates about 0.9 watts. And notice how that's positive. This battery actually dissipates 0.9 watts. It's not supplying 0.9 watts. It's literally dissipating that number. This battery dissipates negative 2.5. In other words, it supplies 2.5. That's what we calculated. And this battery dissipates negative 8.57. In other words, it supplies 8.57. And so negative 8.5, which is 8.5, plus 2.5 is about 11, minus 1, that's about 10. So it is exactly what we calculated. Again, this circuit was a lot easier than it looks. You have to just use the intuition. Not the intuition. You have to just use the thinking about what's actually going on. Where do I have these single currents where I can simplify the resistors? Can I redraw this circuit to make it prettier for me when I do the nodal analysis? Okay. The redrawing isn't even necessary. The primary thing you have to notice was the ability to simplify those series resistors.